All right, so we're going to take a look at some special types of factoring, things that you can look for that are really helpful when you're trying to look for how we break things down into products, because remember that's what factoring means, writing something as a product of its factors, things that multiply to get that product. So today we're going to look at some special things that you can look for that maybe will help kind of guide when you do your factoring. The first one is called difference of squares, and it's exactly what those words mean. So it's a difference, meaning the two terms are connected with a subtraction, and the two things that are connected are all both perfect squares. So I'm going to add the kind of the word that we assume here, but they're perfect squares. So both of the terms are something, a whole number squared or an expression squared. So when we look at factoring difference of squares, what multiplies to give the first is still this first term, and what multiplies to give the last is still that last term. But what's interesting about this, since there's only two terms, that outside plus the insides is actually equal to 0. So they're opposites, right? So there isn't a term in the middle, so that must have added to 0. So that makes it a little bit easier to recognize, because then what multiplies to give us an x squared would be an x times an x. What multiplies to give us a y squared would have to be a y times a y. And the only way to multiply and get a negative number, remember what that meant, if the signs are different, so the signs are opposite, the only way that that can happen, or multiply to get a negative, is if the signs are opposite. So one must be a plus and the other one is a minus. And it doesn't matter which order you write those two binomials in, by the way. It just makes sure that one of them is plus and one of them is minus. They're called difference of squares. When you do the outsides plus the insides, you get a 0. So like in this case, you would get an xy and a negative xy. Well, those are opposites. They're going to add to 0. So it's a nice thing to be able to look for and recognize, but they both have to be perfect squares, and it has to be a difference, a minus in between. That's the only way to have terms add to 0, right? One's positive and one's negative. So let's take a peek and see if this qualifies as a difference of squares, perfect squares. P squared, absolutely, that's p to the second. Is 100 a perfect square? Well, sure, 10 times 10. So when I factor this into difference of squares, how do I get a p squared? That would be p times p. How do I multiply to get 100? Well, that would be 10 times 10, and it's a negative 100. The only way to get a negative when you multiply two numbers is you have one of each sign. Now, if you do FOIL, if you go ahead and do first, outside, inside, last, notice again the OI. The outsides you get a negative 10, and the insides you get a positive 10. Oh, there's the bell. And we would add to 0, which is there's no middle term there. We have no term for the outsides and insides because they added to 0. So difference of squares. I'm going to take a look at letter B. This one's a little different because I don't think 2 is a perfect square, and I don't think 18 is either. But remember what we always look for first. We always look for a GCF first, like a greatest common factor. So I think in this situation, that might be what we need to deal with. So look for a GCF first. Is there something we can pull out front of each of those terms? So each of them has a factor of 2 in there. So what if I pull a 2 out? So 2 times what would give me 2x squared? Well, that would be x squared. And then 2 times what would give me a minus 18? That would be minus 9. So once I do that, look what happens inside there. Oh, for sure, we have perfect squares now. So that's something to watch for. If you don't have perfect squares right away, go ahead and pull out that GCF. So I'm going to have two binomials then. And I'm going to think about what multiplies to give me an x squared. So think about this one and see if you can go ahead and pause the video and see if you can figure out what would those two binomials be if you do difference of squares. So it would be x times x, and then how do I multiply to get a negative 9? Well, I need a plus 3 and a minus 3. So my final factored form would have the 2 out front and then those two binomials. And remember, if you multiply it all back together, you should get back to that original sentence. All right, let's try another one. So difference of squares, that what's a perfect square can be more complicated. Is 9 a perfect square? Yep, that's 3 squared. So is 16. A squared is a squared, and b squared is b squared. So this is definitely a difference of squares. Two terms is the great way to recognize it, right? Only two things with a minus in between. Think about what you square to get each of these. So what do I square to get 9 and a squared? Well, a 3 times a and a 3 times a. What do I multiply together to get a 16 b to the second? Well, 4 times 4 and b times b. So 4b and 4b. And again, remember it's negative, so we have one term that's a plus and one's a minus. You can put the plus and minus wherever because they're exactly the same binomial, so it doesn't matter. Look for what's a perfect square. That's how we're going to be able to tell, and we can multiply those together. All right, let's take a look at this one. Higher powers can also be perfect squares. It doesn't look like it, but we actually can. So y to the fourth, it may not seem like that's a perfect square, but y to the what times y to the what? These things have to be the same. We'll give you a y to the fourth. Well, how about a 2 and a 2? Remember that you're multiplied with the same base, we add the exponents. So if you cut 4 in half, you can get 2 and 2. So any even power actually is a perfect square. So think about if you had y to the 6th, where would that come from? Well, half of 6 would be 3. So y to the third times y to the third. So any even power can be a perfect square. So just because that's not a squared doesn't mean it can't be a perfect square. So I can still do a y to the second and a y to the second. All right, now how do I multiply to get a negative 16? That's a perfect square. What times itself gives you 16? That would be 4 and 4. So again, a plus and a minus. Now what's interesting on this one, so another thing to kind of note over here in our little list of things or strategies to think about, always factor completely. So factor completely means see if you can go further. So like in that one, we had to take out a GCF and then we could do difference of squares. This one, I did difference of squares, but now I think I can go further. This is kind of interesting, but this second binomial, take a look at that one. Is that also a difference of squares? Y squared and 4 is a perfect square, isn't it? So we can actually go further. There is nothing I can do with this first binomial though, so the y squared plus 4 stands. That's not a difference of squares. And why isn't it? Well, it's not a difference, it's a plus. There's no way you can multiply to a positive 4 and add to 0, because to multiply to get a positive, it would either have to be plus plus or minus minus. So there's completely no way I can do that. But the y squared minus 4, yeah, that I can go further. So I'm going to go ahead and move that out of the way here. I'm going to factor that part completely. So I'm going to do more with this second part. So that's where these are coming from. So how do I get a y squared? Well, that's y times y. How do I multiply to get a 4? Well, that would be 2 and 2. And again, it's a difference of squares, so I have a plus and a minus. So I actually end up with 3 binomials as my completely factored answer. So always double check and see, can I do more? Can I factor it further? Because you might be able to. We might be able to break it down further. All right, let's take a look at this last one here. When we look at what's being squared, it's one of those situations like when we did GCF, that what's being squared could be a binomial. All right, so I want you to take a look at this first thing. M plus 3 squared, this is what's being squared. It's kind of like my a squared. It's just that instead of just being a single term, it's an m plus 3, but that's what's being squared. Is 49 a perfect square? Sure, 7 times 7, and so z. So when we do this, I know it's going to look super goofy, but what goes in this first position is what's being squared. So it's just the m plus 3 in each of those first positions. And then what do I square to get a 49z squared? Well, 7z times 7z. And then it's subtracting. So how do I get a subtraction? Well, it's a plus and a minus again. So I know it looks a little goofy, but you can square binomials as well. Those are called difference of squares. When you have two terms, they're both perfect squares and they're being subtracted. It's kind of a special kind of factoring that we're going to look at. All right, so another one, which is very similar, is called perfect square trinomials. So what happens in a perfect square trinomial is that both of the binomial factors are identical. So in the last one, they were almost identical, right? We had one that was a plus and then one that was a minus, so in our two binomial factors. In a perfect square trinomial, both of the binomials are identical. So I want to go ahead and do FOIL so we can see what that's equal to. So a times a would be a squared. Outsides we get an AB, insides we get an AB, so together that's 2AB. And then plus b times b would be b squared. So a perfect square trinomial just means you have the same binomial multiplied times itself, and you end up with this trinomial, 3 terms that came from a perfect square, so something squared. That's all that means. So now the second one is identical, except for their minus minus, so still two binomials that are the same. But what's going to happen when you do FOIL on this one, see if you can guess. Instead of plus 2ab, when I do insides and outsides, it's minus 2ab. But what happens for the last? What's a negative times a negative? That's going to be a plus. So the only difference is the difference. Get it? Pun intended. So perfect square trinomials are just a binomial times itself. If you can recognize that that's what they are, if you see trinomials where your first term and your last term are both perfect squares, this is a good thing to check for because it makes it a little bit easier to factor. All right, so let's take a look and see if we can recognize a couple of these. So first of all, how I recognize a perfect square trinomial is that there has to be 3 terms. So 1, 2, 3. Have 3 terms. And then I check to see, hey, are these first and last terms something squared? Now 49 is a perfect square, z squared is a perfect square. Is 1 a perfect square? Well, yeah, Yeah, because 1 squared. So one thing I would try in my binomials is see if I can factor it like these. Now let's double check and see what's going on with the signs. The middle term is a negative, the last term is a positive. That means they're multiplying to a positive and adding to a negative. All right, so what does that mean for my signs? Well, that means I have to be in this bottom situation that has to be both negatives if those signs are like that. And that's the same as any other factoring we've ever done. That is not new, so fill in what we know. How do you multiply to get a 49? Well, because it kind of looks like this is a perfect square thing, I'm going to guess 7. So 7z and 7z. How do I multiply to get a 1? Well, there's only one option. It's prime, 1 and 1. So notice my two binomials are the same. Now, is this the right set? Well, outsides plus inside should give me that negative 14. So I have a negative 7z and a negative 7z. In other words, that middle term is always double whatever that inside or outside product is. There's like two of the same terms, so they just double. That's where that 2 comes from. So checks out perfectly. We get that negative 14. So if you see perfect squares in your trinomial like that, it's a good thing to try. Instead of listing like all the multiple things that multiply to get 49, let's try the perfect square one first because it might work. All right, let's take a look at this one. Also a trinomial, yep. So let's look at this. Double check for GCFs. There wasn't on the last one. 9, 48, and 64. Do they have any things in common? Well, 9 and 48 do. They have a factor of 3, but 3 doesn't divide into 64, so I think we're kind of sunk on that, but good thing to check for. It is a trinomial, so it's going to factor, if it does, into 2 binomials, so I know that. Look at the first and last term. Do they look like they're perfect squares? Sure looks like it, because this looks like it's 3a being squared. What squared gives you 64? That's 8, so it kind of looks like that might be an 8b squared. So I'm going to give this perfect square trinomial a shot where both of the binomials are the same. So I'm going to see if that works. So 3a and 3a, because these are big numbers, like 64 has a lot of factors. So if it's the perfect square option, all the better. Multiply to a plus, so I know the signs have to be the same, and the middle term adds to a plus, so they both have to be plus. So notice again, perfect square trinomials, we're doing this first case here, both of the binomials are identical, they're exactly the same thing. Let's check your outsides. So 3 times 8 would be 24ab, and then another 3 times 8 would be another 24ab, and we add those up, we get our 48ab. I have that middle term that I was looking for. So it's something to watch for. If you just did normal factoring and thought, hey, what are all the ways I multiply to 9 and 64 and did everything, you'd eventually get there, but you might be able to be more efficient if you do it this way. All right, the last thing we're going to talk about today is difference and sum of cubes. So we haven't really talked about things that are cubed yet. We've really focused on the squares. So we're going to talk about perfect cubes. So we're going to do difference of cubes and sum of cubes. So what would be helpful, kind of have a list here so we can keep track of some perfect cubes so we know what's happening. So can you take a moment, pause the video and fill that in? Just go ahead, use your calculator, fill in this perfect cube chart so you have the numbers there so you can recognize them when they happen. So pause the video, go ahead and fill those in. So 2 cubed, 2 to the third is 8. That's 2 times 2 times 2. 3 cubed is 27, 4 cubed is 64, 5 to the third is 125, 6 times 6 times 6 is 216, and then 7 times 7 times 7 is 343. Usually we probably won't go higher than that, but if you need to figure out bigger ones, we sure can. This will just be a nice resource. Okay, so there's a formula for difference of cubes. It's helpful just to be able to look it up and work with it and know it's always going to be a binomial times a trinomial. So that's kind of the format for it. Difference of cubes means you have 2 terms that are perfect cubes and there's subtracted in between. So a difference of 2 things that are cubed. That's where this is coming from. So it's a minus b, so what you're cubing for each of them, and then a squared plus ab plus b squared. Now, I'm not going to spend the time right now going through and multiplying this out, but if you do your distributive properties, so if you multiply out all of those terms and all of these terms, and you add all of your like terms together, what you end up with is only the a cubed minus the b cubed. So think of it sort of like a formula that we can substitute in for. We really just need to know what a and b are, and then we're going to be able to just fill in what that looks like. And we can check our answer anytime because we can just multiply it out and see if we have the right thing. So the key is figuring out what's being cubed. All right, so let's take a look at letter A. How do I know it's a difference of cubes now instead of a difference of squares? Well, right away I see a 3 instead of a 2 for my exponent. Remember when we did these difference of squares? We started with like a p squared, right? Perfect square. We're looking for cubes now. So when I see this, And then it's making me think difference of cubes. Now, the other thing to check for, and our list didn't go up this high, is 1,000 a perfect cube? So now if you're not sure, we can use our calculator here. I'm going to go under the math menu. See where it says cube root, that number 4? How about we try taking the cube root of that number and just double checking? What number times itself 3 times gives me 1,000? Well, 10. Absolutely, it is a perfect cube. So if you're ever not sure, you can type it in. So think of this like it's the x being cubed minus a 10 being cubed. If you can think of it that way, then we know, and you can think of it more as a formula, what my a value is in this formula and what my b value is. My a is the x, what I'm cubing in that first position, and my b is the 10. So what I'm going to have you do is just go through this formula and just replace everywhere you see an a, we're going to put an x. Everywhere you see a b, we're going to put a 10. So we have a binomial and a trinomial. So we have a minus b. Well, a is x and b is 10. And notice you've got to follow the signs the way they are. That's how our terms add and add up to what we need to have for a cubed minus b cubed. All right, now we need an a squared. So I'm going to take the a, which was x, and I'm going to square it. So x times x. Plus, I'm going to multiply the a times the b. So the 10 times the x, and I think the easiest way to write that would be 10x. X times 10 is the same thing, but it looks a little wonky. And then the last term is plus b squared. All right, that means take the b value and square it. So 10 squared. Now, for me personally, I don't usually leave it 10 squared because that seems kind of goofy when I know I can figure that out. 10 squared is 100. Now, that's the factoring for x cubed minus 1,000. Now, if you wanted to prove it to yourself that it actually works, you would go through and do this arithmetic and check and see that what you get is just that x cubed minus 1,000. All right, so just so we can talk about it for this first one, I went ahead and did the distributing so you could see what happens. So the green is distributing the x, and then the blue is distributing that negative 10, and watch what happens. When I do that and I put my like terms together, the 10x squareds add to 0, the 100x's add to 0, and all you have left is an x cubed and a minus 1,000. So we do get back to those terms. So that difference of cubes formula is how we're working backwards to get that. So I know it looks a little goofy, but those are the terms that we need. Those are the factors we need to make that difference of cubes. So your job again is to figure out what those different values are. So being able to substitute those in. So it's kind of a nice way. Sometimes it's helpful, oopsies, just to think of this format, right, and be able to solve. So that's what we did here when we, oh dear, when we were writing this out. So hopefully that kind of line up to think about what's going on. So let's try that for one more so we can see what's happening for each one of those. All right, so let's see if we can figure out if this is truly a difference of cubes for letter B. So for the first one is 27 something cubed. So this 27 m to the third, well, that looks like 3, right? Cubed is 27, and m to the third would be m cubed. So that looks like it's a perfect cube. How about 64? Is that a perfect cube? Sure is. That's 4. So 4n must be cubed for this one. So I'm going to kind of lay out the format here. So I have the formula. So my a in this case, lowercase or uppercase, doesn't matter, is this 3m. And my b is the 4n. Actually, if I follow the color coding here, I'll try to do that. So the b is the 4n. Those are what's being cubed for each one of these. So my a cubed minus b cubed. So I have, think of it like this, 3m cubed minus the 4n cubed. And here's our format. So we have a binomial always times a trinomial. So we take our a value, which is the 3m, minus our b value, which is the 4n. So it's just a minus b. And then we have, in the first part here, a squared. So that's going to be 3m squared plus a times b. So 3m times 4n. And then plus our b squared, which is the 4n squared. Oh dear. So 4n squared. Notice when I write the squaring, excuse me, I use parentheses because if we have a term with multiple things inside, excuse me, we want to make sure that we are squaring everything that's in there. So I'm just following that format. The more complicated your expressions are, the more terms you're going to have to deal with. All right, so we've got this 27m cubed minus 64n cubed. What would that actually be then? Well, the binomial is always fine. So 3m minus 4n, binomial. The only other things that I would kind of clean up a little bit is in this trinomial, 3m squared, 3m times 3m. That would be 9m to the second. A really common goof people make is they'll say m squared, but they forget to square the 3. Use the parentheses. Think about what it means. That whole term is being squared. In the middle, I can multiply those together. 3 times 4 would be 12, and then m times n. And then in our last term here, 4n times 4n, that would be 16n to the second. So don't forget, again, you've got to square the 4. So think of it almost like following a format, following a formula where you're trying to write out what those would be. Now we can do sum of cubes as well. It's very much the same idea. So we're going to finish up with practicing a couple sums. The formula is almost identical. So you'll see when we write that out. So make sure we get the formula here. It's again a binomial times a trinomial. And it's just a plus b for the first one because it's a sum. So notice both things are cubed and it's a sum. A squared minus ab plus b squared. So the only difference, if you look and compare those two formulas, I'll go back to the other one, is where the minus and plus signs go. In the difference of cubes, the minus is in the binomial. In the sum of cubes, the difference is in the trinomial. So otherwise, though, it's exactly the same. So we're looking for things that are perfect cubes, and then we can multiply that out. Now let's take a peek at this first one. I want to bring you back to some of the things that we did before. Is 2 a perfect cube? It's definitely not on that perfect cube list. And 2,000, if we try that on our calculator, so you could go back and use that same thing we did before. Go to your math key, number 4. So let's try it. Is 2,000 a perfect cube? Well, no, you got a decimal answer. So what that might mean if you're seeing cubes like that is what we had to do before. Look for a GCF. Is there something I can pull out of both of those terms? Well, each of them are even. So how about pull out a 2? That would leave me with x cubed plus 1,000, right? 2 times x cubed would be 2x cubed. 2 times 1,000 would be 2,000. Now are they both perfect cubes? Absolutely. So this is an x being cubed, and this is the 10 being cubed. We already did that in one of those last examples. So when you think about our formula here, it's like our a value is the x, and our b value is the 10 again. So this is going to look super similar to that one that we did before. So this is a binomial times a trinomial, but with a factor of 2 out front. So that's still part of our product, because remember, factors mean when I multiply them back together, I get back to that original. All right, so let's follow the formula. So it says, say, take the a plus the b. Well, the a is x and the b is 10. And notice it's a plus sign because that's where those signs need to be to get that sum. And then inside, the a value squared. So x squared. And then minus, so that is a subtraction. Follow the signs in the formula, the a times the b. So the x times the 10. So I'm going to write 10x because for me that's easier. And then plus the b squared. So the b value was 10 and I need to square it. So once again, I probably wouldn't leave it 10 squared. I know some people do. For me, I know what 10 squared is, so I would probably just write that as 100. If you look back to our one that we did that was, I think, p squared plus 1,000, your answer is super similar. The only differences are the signs, and then we have this factor of 2 out front. So we need all 3 of those. All right, let's try one. Oopsies. I guess we're going to do 2 more, but let's see if I can move this up a little bit. All right, so let's take a look at this letter B. So I want to see if these are perfect cubes or not, and sometimes it's helpful. Some people like to look at that format, so I'll try that on this one if that's helpful. Is this a perfect cube? 8 for sure, so that's 8 or 2p being cubed. Is 125 a perfect cube? So look back on your chart here, 125. Oh, yep, sure is. That's a 5. So that's going to be a 5 cubed. So it's definitely a sum of cubes. And how do I know it's a sum? Plus sign in between. All right, so that means like my a value, maybe I'll try to color code here a little bit more. My a value is that 2p. That's what's being cubed in the first position. And then my b value is the 5, because that's what's being cubed in the second position. So when I'm thinking about what's happening here, think about it as you're taking a 2p and cubing it, and then you're taking a 5 in cubing it. And it's the sum of those two things. So the a cubed plus the b cubed. All right, so remember how that factors then. We have a binomial times a trinomial. I'm going to need to have a little bit more room here, so I don't write as small as what they do. I'm going to go ahead and fill in the signs. I'm going to be adding. It's going to be a minus and then a plus, so we can fill in all of the blanks here. All right, so it starts with whatever a is, and a was 2p, so my first position there is just 2p. That's what I'm cubing to make that first term. And then I have plus b. All right, well, b was 5, right, because that was what I cubed to get the second term, so plus 5. And then inside the trinomial, a squared, that's the first term, which is 2p, and then squared. The middle term in this trinomial is a times b, so 2p times my b value, b is 5. So 2p times 5 in the middle, and then plus b squared. Well, b is 5, so 5 squared. So the only things we're really doing is trying to clean up a little bit, I guess, what's going on in that trinomial. So for this first binomial, we're good, 2p plus 5. And then let's clean up the trinomial a little bit. 2p squared, so 2p times 2p, that's what you need to think. So 2p times 2p, 2 times 2 is 4, p to the second. Minus 2p times 5, so 2 times 5 would be 10, so 10p, and then 5 squared is 25. So when we're looking at simplifying there, just try to see if we can put together some of those things to make it a little bit easier to read. All right, so I'm going to have you give this last one a whirl. So we've done a bunch of cubes now. I want you to see if you can figure out what are you cubing for each of these terms. So what would be your a and your b, and see if you can follow the formula and plug those values into the right spot. So look at this first term. What are you cubing to make that happen? Take a look at the second term. What are you cubing to make that happen? And notice it's a plus in between. So go ahead, pause the video, see what you can come up with. All right, so what cubed is 64? Well, that's an 8, or pardon me, a 4. Help me. Perfect squares can get confusing with perfect cubes, so just keep your thinking straight. I need to do that too. So 4, and then m, right? M cubed would give you m cubed. What do you cube to get 125? Well, that's a 5, so that would be a 5 and an n. So your a value, like in the formula here, your a is the 4m, and your b is the 5n. All right, so we're going to see if we can write out this expression. So we're going to have our a cubed plus b cubed is equal to a binomial times a trinomial. All right, so I'm going to kind of move this down here so we have our values. I know it's a little bit funky here because I have to write a little bit bigger. So our a cubed plus b cubed, then that means we're doing 4m is our first, that's our a that we're cubing, and then our 5n is our b, and that's what we're cubing, and then remember this is a sum, so it's plus. All right, so I'm going to fill in all the signs. So I know it's going to be a plus, a minus, and a plus. Kind of helps me separate what I need to do. All right, first term is an a. A is 4m, and then plus b, which is 5n. And then in the trinomial, the first one is that first term squared. So 4m squared. In the middle, it's a times b. So 4m times the b is 5n. So we're multiplying those together. And then plus b squared. So 5n squared. All right, so we're going to simplify everything inside there. So we're going to go ahead and simplify what's going on. So we've got a 4m plus 5n. That was fine. What's 4m squared? So remember what we're thinking there. That's like 4m times 4m. So 4 times 4, 16. M to the second. Minus 4 times 5 would be 20. M times n, just mn. I like to write them alphabetical. That's for me easier. And then 5n squared. So that means 5n times 5n. So 25 n to the second. So these formulas for sum and difference of cubes is really a matter of just figuring out what's being cubed, and then you're just replacing. You're substituting in for those values. So when we look at 64 m to the third plus 125 n cubed, if I multiply these two factors together, I will get back to that. And again, you can check your answer. It's just kind of a lot of arithmetic. If you know you followed the formula correctly, we should be in good shape. All right, so special kinds of factoring. So we talked about difference of squares, perfect square trinomials, difference of cubes, and then sum of cubes. All great things to be able to recognize.